Hello everyone, welcome to week 6 of problem solving session for NPTEL course uh, Introduction to Operating Systems. And in this week we have looked at synchronization, and today we are going to look at quiz type questions related to synchronization. So let us get started. And so here the first question is, which of the following conditions could occur due to lack of synchronization? First one is inconsistency, loss of information, deadlock, all of these. So here, um, if there is no synchronization, then it is possible that multiple processes will access the shared resources, or we can also call it the critical section at the same time. And when they access the shared resources or shared data at the same time, then it can lead to inconsistency, because more than one application can be, or more than one processes can be simultaneously modifying the data, so which leads to inconsistency. And also loss of information, because it is possible that one process wrote something and other process overwrites it, so information is also lost. And deadlock is also possible in cases when either there is no synchronization or synchronization is not uh, has not been implemented correctly. So it is possible that multiple processes will try to access the same resource and they will deadlock. So all of these are possible due to lack of proper synchronization mechanisms. Now moving on to the second problem, it says that a critical section is a program segment, first, which should run in a certain specified amount of time, second, which should avoid deadlock, third, which must be enclosed by a pair of semaphores P and V, and fourth, where shared resources are accessed. So if we look at the options one by one, first, which should run in a certain amount of time, this is incorrect, because critical section doesn't mean that it can only run within a specified amount of time. Second, it should avoid deadlock. This is not the responsibility of the critical section to ensure that there is no deadlock. We need to have additional mechanisms to ensure that there is no deadlock. Third, it must be enclosed by a pair of semaphores P and V. So yes, we use semaphores to for synchronization, but that is not required. It is not a requirement for a critical section. Okay, and the fourth one is where shared resources are accessed. This is a correct this is correct in terms of critical section, because the critical section is that program segment where shared resources are there, and the processes, and we need to ensure that the processes do not access the shared resources at the same time. Okay, so the problem here, uh, problem number 3 is, consider the following code comprising of a swap function which is atomic. And so the swap function here is taking two Boolean pointers and A and B, and then it is just going to swap those two values. Okay, but it is saying that assume that it is atomic. Atomic means that this will execute as a one instruction, you can say that, and that's it's atomic. Then this on this side, if you see that there is a global variable which is locked, which is initialized to false, and then there is this code for processes. So it takes as parameter I, which indicates the process ID here, and then inside this you have one local variable key, which is Boolean, and then you have the while loop, indefinite loop, and in this you first set the key to true, Then there is while loop, which is of checking the value of key, and if it is true, then this while loop condition will be true, and then swap function will be called. The swap is given two parameters. First is the lock variable, second is the key. So swap is atomic, right? And this will atomically swap the values of lock and key. After that, if uh, this is the lock here, this section comprises the lock here, and if the lock is acquired by the process, then the process will enter the critical section, and once it has finished executing in the critical section, it will release the lock. For that, it just changes the value of lock variable to false. Now this is the code which has been given to you, and the question is asking that the above code does not provide first mutual exclusion, second progress, third bounded wait, and fourth the code snippet solves the synchronization problem. So I'll give you some time to think about it. Oh, I'm sorry. Okay. Yeah, so this question I'll repeat again. So the question here is so you have been given this code which has a swap function and which is atomic, and on this here you have this process function which is like for a process, and you have this global lock variable which is initialized to false. Inside the process function you have another variable key which is local to this function, and it has a infinite while loop, and the infinite while loop, inside that you have first statement is key equal to true, then you have that if key is equal to true, then you take the values of lock and key and swap them using the swap atomic function, and if the lock is acquired by the process, then the process enters the critical section, and when it exits the critical section, then it will unlock. So to unlock it, it sets the value of lock to false. So now the question here is asking that the above code does not provide first mutual exclusion, second progress, third bounded wait, and fourth the code snippet solves the synchronization problem. So which is the correct option here? You can take some time and check all of them, whether so take two processes and see if this code here achieves mutual exclusion or not, and then progress, and then bounded wait, and then you should answer that whether this code does not provide any of these or not. Any thoughts and ideas? So it doesn't, you're saying it doesn't provide one or three. How can you uh, try to explain why it doesn't provide one? Sure. Okay, no problem. I will see. 1 second. I will share. Can you see the slides now? Okay. And can you see the whiteboard also? Okay. Okay. So this is. Okay, so this is your code, right? And so let us first see that how mutual, why, like whether it provides mutual exclusion or not. So for that, let us take two processes, P1 and P2. Okay, so both of the processes have the shared variable lock here, which is initialized to false. So this is shared between both of the processes. And now why this is shared? Because it is global here. Now each of the processes, process 1 and process 2, they have a local variable key. Okay, so here just although the variable here is key only, I'll just call it key 1 and key 2 because that will just make it less confusing. So they both have two variables, uh, key, okay, and then we have an infinite loop here while in the while loop we set key equal to true. So let's say if process P1 is executing and process P2 is not yet started. Okay, so if process P1 is executing, it starts key equal to true. So we will set here key equal to true. After that, it has the statement while statement. Okay, while statement is key equal to true. While key equal to true, swap lock and key. So here key is equal to true. This condition is true. So swap will be called, and swap. So swap lock and key. Now here lock value is false and key one second. Okay. Okay, here swap lock value is false, right? And key is true. So when you will swap the values, what will happen? When you swap the values, then lock will become true and key will become false. So now your global variable here lock value is true and key value, I'll just write above only, this becomes false. Okay. After this, your process P1 will enter in the critical section, and once it has finished the critical section, it will set the lock to false again. This is how your process 1 will execute. Okay, once. Now let us look at now let us look at, I hope if this is clear, if not just let me know. Now let us look at if two processes are simultaneously trying to access the critical section, then what will happen. So there is process P1 and then there is process P2. Okay, so process P1, and there is, we have the common variable lock. Okay, and lock is initially false, means nobody has locked the critical section, it is free. So when process P1 executes, it will set its key initially to true, and also process P2 will set its key to true. Okay, after that both of the processes will try to enter the critical section. So to enter the critical section, both of them will execute this while statement here. That is, they're going to check their key. If their key is true, then they will swap the lock. So when they try to, so what will happen in process P1? Process P1 will find out that it will check its key, it's true. So it will call the swap function. Okay. And similarly, process P2 also, let's assume that we'll write the statements here. So let's write the statements here. First, while key 1 equal true, here while key 2 equal to true. Let's say that both of them simultaneously are checking their key value, and both of them are true. So both of them will be true, right? After that, if both of them call the swap function simultaneously, it calls lock and key 1, and it also calls lock and key 2. I mean its value. Okay. Now the swap function is atomic. So that means that the swap function, whenever it is called, it will be executed as one instruction. So when process P1 calls this swap function, it will swap the value of lock and key 1. So it will be changed in, it's like just one instruction. So okay, so when this is executed, it will be changed to false here, and it will become here true. Now if process P2 also calls the swap function here, then it will try to change this value of lock and key2. So lock value currently is true and key2 is also true. So, when it will swap the values will be swapped, but the values will still be true, true only, because the lock value is currently true. So since here, now what will happen? Now in this case, in process 1 case, it will go back and check the value of key 1. So key 1 will become false, means it will come out of the while loop and it will start executing the critical section. But in case of process 2, it will go back to check its while condition. The while condition will still be true because key 2 is still true, it's not false. The swap happened but the lock was true, so after the swap key 2 is still true, and therefore the while loop will still, condition is still true, and it will continue to execute the while loop. It is still busy waiting and it is not going in the critical section. Only process P1, which executed the swap instruction first, that process is here going to the critical section. So this here, so only one of the processes was able to go to the critical section, execute the critical section, hence it ensures mutual exclusion here. Now progress in, so whenever this process P1 finishes execution, and it will then set the lock value to false. So here lock is equal to, I need not write this, but here this false statement will be executed. Then at that time this value will be changed back from true to false here. And when this value is changed back from true to false, and if process P2 is still in the loop here because it is still trying to enter, so then it will swap the value of key 2 and false, and when it will swap the value of key 2 and false, this will be set to true and key 2 will be set to false, and then this while loop will become, condition will become false, and at that time it will enter the critical section. So there is progress. Progress just means that if the critical section is empty and if a process is trying to enter the critical section, then that process can enter the critical, is allowed to enter the critical section. So, there is progress here. Is that clear? Okay. Now the third one is bounded waiting. Bounded waiting means that there is a bound on the number of times, uh, the process has to wait. Number of times the other processes are allowed to go in the critical section since the process has arrived. Right? Like the waiting time of a process is not indefinite. It doesn't starve forever to enter the critical section. So what do you think about bounded waiting here? So here If we take the case of these two processes, then I have just explained, if process P1 was executing, if both of the processes are contending for the lock at the same time, then one of the processes will be allowed to enter the critical section. Mutual exclusion is ensured. So here in this the example I gave, process P1 first executed swap function, so it entered the critical section, and then when it released the lock, then process P2 here was executing, say, this code here. It was busy waiting on this code, so it was able to execute the swap instruction here, or the swap function, and it was able to enter the critical section. And there is progress here, because even if P1 have entered the critical section and it left, if P1 again wants to enter the critical section, then it can still do that. It doesn't have to wait for any other process. Or if the critical section is empty, then the process which is waiting for critical section will be able to enter it. Now, bounded waiting, here bounding waiting just means that there is a bound on the number of times the other processes are allowed to enter the critical sections after a process has made request to enter its critical section, and before that request is granted. So if we take this example of only two processes here, then if P2 has requested to enter the critical section and P1 is already in the critical section, then as soon as P1 leaves the critical section, P2 will be able to enter in the critical section, because this is already busy waiting on the lock. However, if there are n number of processes and say P1 to Pn, then it is not clear that how this solution here does not ensure that there'll be bounded waiting, because there is no order in which the processes, there is no ordering here in terms of which process can enter in the critical section. So if there are n processes, then if P2, P3, P4, P5, four processes have requested to enter the critical section, then one of them will be allowed to enter the critical section as soon as the lock is available. But which one? And there is no ordering ensured by this code, and it doesn't ensure that no process will wait indefinitely. So in general, this code, I think, does not provide bounded waiting, but since for two processes it does, and as per your question here, the above code does not provide, if we try to answer it. So it provides mutual exclusion, this is true. It provides progress, which is true. And uh, so bounded wait, it doesn't provide in general for multiple processes if there are n number of processes. So hmm, do you have so is it clear to everyone, or is there any other question? Okay, if there's no question, okay, hope that was clear. Then the problem number 4 here is, in the bakery algorithm for synchronization, if two processes have the same token, then the process with lower process number enters the critical section. thoughts or ideas? Okay, so bakery algorithm was covered in the course. It's there in the lectures. I hope you have gone through it. Can you try to answer the question? If in the bakery algorithm for synchronization, if two processes have the same token, then the process with the lower process number enters the critical section. True or false? So the bakery algorithm actually gives a token to every process, and the process which has the smallest token value is allowed to enter in the critical section. And so in case if two processes have been given the same token, then to break the tie between those two processes, their process IDs are compared, and in any system it is ensured that the process IDs or the process number are always unique. So since process number is unique, so the process with the lower ID, lower process number, is allowed to enter the critical section. So this answer to this question here is true, that in case two processes have the same token, then the process with lower process number enters the critical section. Okay. Then the next problem here is Peterson's solution is a synchronization mechanism which works for a maximum of dash processes. So if you've read the Peterson solution, so the question is asking that uh, how many processes does the Peterson solution work? Any answers? Oh, sorry, I was not checking the chat. Uh, Highest ticket number. Okay, that. Yeah, the token numbers are compared with each other, or I think you're calling that ticket number. So they're compared with each other, and the process which has the smallest token number or the ticket number is allowed to enter in the critical section. But the question here is saying that if two processes have the same token or the same ticket number, say both the processes have token number 2, then the which process, how will you break the tie? Which of those two processes will be allowed to enter the critical section? So in the bakery algorithm, uh, which has been explained in the course slides also, the process with the lower process number. So since every process in your system has a unique process number, unique process ID, so if process P1 and P2 both have the same token number, then process P1 with say will be allowed to enter the critical section because P1 has say lower ID, lower process ID than process P2. Is that clear? And yes, this is right. So Peterson's algorithm works only for two processes, while bakery algorithm works for multiple processes, more than two processes. Both of these algorithms provide mutual exclusion progress bounded waiting, but Peterson's solution only work for two processes, while Bakery algorithm works for more than two processes. Okay. Okay, next problem is, if the value of a counting semaphore S is equal to 5, then the maximum number of requests for the critical section before it blocks is. So you're given here a counting semaphore. So there are two types of semaphore: binary and counting. Binary semaphore can take only values 0, 1, while counting semaphore uh, takes an integer values. Okay, it can take integer values. So initially you said here in the question that your counting semaphore has value 5, and then the maximum number of requests for the critical section before it blocks is. So how many requests can be made which will successfully enter the critical section? Yeah, that's right. So 5 requests can be made. So here S is equal to 5. Okay, so when first request is made, then S on every request your semaphore is decremented. Okay, so it will become then 4. Then you can make next request. So you can make 5 requests here, and because your semaphore value is 5, and after the fifth value, when the value becomes -1, at that, so when your semaphore value is 0, and if you make another request to enter the critical section, then the value will become -1. Okay, that means that one process is blocked. One process is blocked from entering the critical section. So there is a process which is waiting to enter the critical section, but the semaphore value has become negative and it is not allowed to enter the critical section now. So 5 processes will be allowed to enter the critical section here before it blocks. Yeah, it is decremented by 1 on every request. Okay, great. If there is any question, then you can ask. Okay, next one is context switch cannot happen while a process is executing critical section. So if a process is already executing in the critical section, then can there be a context switch or not? True or false? I False. Okay, so what is a context switch? Switch from one process to another. That's right. So context switch means your process is running and then you move that process from running state to say ready state or any other state, and another processor scheduled in the processor. That is context switch. Uh, so here it's saying that context switch cannot happen while a process is executing critical section. It's true or false? Well, it's so one answer is false, one is true. Okay, so a context switch can happen. Actually, there is so you've been so there are different ways actually. Like if interrupt is disabled before entering into the critical section, then the process will not be, say, there will be an interrupt won't happen and the process will only be preempted or removed after it has finished the critical section. But that is only that solution does not work on multi-cores, and so in general this statement is false. sorry, yeah, the statement is false here because context switch can happen. Okay, if a process P is executing, we'll go back here just to for some visualization. If a process P1 is executing here, and if another process is there, that process can be scheduled. If like okay, I'll just go here. If you had these two processes P1 and P2, if P1 is executing in the critical section already, and if P2 process say it arrives and the process starts, it arrives, okay, it's in the ready queue. And so think of round robin. Just because your code that has critical section, your process, it's not like that the OS will stop the round robin scheduling, right? If P1 is allowed to execute only for say 2 time units, and P2 is also allowed for 2 time units because the round robin quantum is say 2 units, then P1 will be allowed to execute for 2 units. Even if it is in critical section, it will be removed from the processor, and P2 will be given chance to execute. Okay, and now since P2 has been given a chance to execute, but P2 might be just busy waiting for the lock. That is fine. It is wasting the processor cycle, but P1 can be removed from the processor even when it is executing in the critical section. And that is why synchronization mechanisms are important, because if there was a guarantee that process P1, if it is executing in the critical section, it will not be removed from the processor, and there is only one processor, then we would not need synchronization mechanisms. Okay, because the process will enter the critical section, it will finish everything executing the critical section, and only then it will be removed. But since there is a possibility that another process will again also be simultaneously scheduled, it can be P1 can be removed, P2 can be scheduled, and P2 can try to enter the critical section while P1 was earlier executing and it has not finished the critical section. So to avoid those inconsistent situations, synchronization mechanisms are put in place. So in short, the answer is that if a process is executing in the critical section, it can be removed from the processor and another process can be scheduled. Is that clear? If not, if you have a follow-up question, you can ask that. But a process can be removed from the processor even when it is executing in the critical section. So this is false. Okay, moving on. Consider a program which spawns 10 threads to find out the sum of all elements in a shared array of 100. So you have an array of 100 elements and there are 10 threads. Okay, and you have spawned these 10 threads to compute the sum of all the elements in the array. The array is shared among all these threads. Okay, each thread I takes elements ai to a of 10 into I minus 1. Okay, so the first thread is going to take the uh, is going to take say from a1 to a of 9. These elements will be taken by the first thread, and then it computes a local sum. It computes a sum of only these elements, and let's call this L sum I. Okay, local sum I, and eventually adds local sum I to a shared variable total sum. Okay, every thread here is computing a local sum of the elements that it of these elements. Okay, and then it is taking that local sum and adding it to the shared variable total sum. Which of the following needs to be placed inside a critical section? First, reading array values, adding to total sum, both of the above and none of the above. So it's asking which of these two operations, reading array values, adding to total sum, both of the above, none of the above, will you put in the critical section? So any answer? Is the question clear? So the question is saying that you have spawned 10 threads. So if you recall, then threads are is the execution unit smaller than process. They share the process address space, and we use threads to uh, to incorporate parallelization in the process to do multiple tasks at the so the process multiple tasks can be done. Okay. And so here you're using threads to compute the sum of elements in a array of 100 elements. So there are 100 elements, you have spawned 10 threads and you're giving about 10 elements to each thread, and each thread is going to sum only the elements it's given to. Okay, and then it's after it has computed this local sum, it is going to add this local sum to a shared total sum variable. Okay, now this, so its question is asking which of the following needs to be placed inside a critical section. Okay, I'll just draw it so that it becomes more clear to you. And 1 second. So it's like if this is your array, okay, and we are going to divide it into 10 parts here. This is your array of 100 elements, okay, and each part here, let's say, is 10 elements. It's a group of 10 elements. So what you have done, what has been told to you in the question, is that you're going to take a thread and give these elements. So it's, let's say you give to thread 1 you give these first 10 elements, then to the thread number 2 you're going to give the next set of 10 elements. Okay, now thread 1 is going to take these 10 elements, it's going to do this local sum, that is add. It is going to add these elements, say in the array A, from 0, sorry, I should use the notation, just say I, from I equal to 0 to 10, 9, right? So it is going to take these elements and it is going to add them, and that is the local sum. That is the local sum for the threads 1. So I'll just say local 1. Not here, this should be I only. Sorry. Okay, so this is local to this thread, and similarly this is going to compute a local sum which is sum of elements from I equal to 10 to I is equal to 19 and A of I. Now, all of these threads are going to access their elements, which are 10 elements, and they're going to sum them. Now here, thread 1 is reading elements from this array. Okay, it only reads elements from this array, not write anything to the array. So whenever we read anything from a shared resource, we do not need to uh, protect the accesses. So since read does not change anything in the shared resource, multiple processes or multiple threads can be allowed to read the shared resource at the same time. That's first thing. Even if they were reading the same from the same location, reading is allowed. Reading is okay because reading does not modify the resource. So both of the threads here would be reading the same value. But in this case here, thread 1 is accessing only these elements, while thread 2 is accessing the next 10 elements. So anyways, the set of elements are mutually exclusive to the threads. So they are disjoint to the threads. Okay, they're not sharing the elements that they're accessing. So since they're not, although the entire array as a whole is shared among all of the threads, but the threads individually, they are accessing only some region of the array which is specifically assigned to that thread. So first, the first reason that reading the first operation, which is the here, is reading array values. This is not placed inside the critical section, and the first reason is that the reading operation doesn't need to be put in the critical section as such, because reading does not modify the resource, the data. Okay, and second, also because even if they were modifying the array, still they would not be need to put in the critical section, because each thread here is accessing only a unique part of the array. Okay, so it is unique. So that is why the first here, the first operation, which is reading array values, is not placed inside a critical section. The second one is adding to total sum. So once they have computed this local sum, they're going to take this local sum and they're going to add it to some global variable. So global variable would be here, say total sum, which will be initially 0. Okay. Now I should improve my writing. It is initially here 0. Okay, I'm just assuming here, let's say the sum here turns out to be 10 and sum here turns out to be say 20. Okay, now now if we do not have synchronization, that is if both of them are allowed to access the total sum variable at the same time, then inconsistency can occur. Okay, or lack of data can occur here. How? I think you have already seen this as an example in the course lectures, but what can happen is that this thread is going to read the value of the total sum as 0. At the same time, thread 2 can also read the value of the local sum as 0. Now it will take the total sum value as 0 and then it will add value 10 to it, and so that will come out to be 10, and then it will try to update this with value 10 here, and it would have updated it with value 10. But before that update, thread 2 has already read the value of total sum as 0. So it will also take the value 0, add 20 to it, and now it will think that the total sum now should be 20. So it will now update it to 20. Although the total sum should have been 10 plus 20, which is 30, but the update would have changed it to 20, rewritten it to 20, which is wrong. So that's why the total sum is, since it is a shared variable here, and access to the shared variables needs to be uh, properly synchronized. That only one thread at a time can access the total sum variable because it is being modified and it is shared. So the answer here is adding to total sum. This operation will need to be put inside the critical section. Is that clear? Any doubts? Hmm. Okay. Uh, okay, if there is any question, you can ask me. Otherwise, I'm moving to next problem. When a process exiting a critical section calls wake up, all the contending processes wake up at once. This is called dash, and that it can be solved, uh, and dash can be used to solve this problem. So there are four options here. First is thundering herd problem and process queue, lost wake up process queue, thundering herd semaphores, and lost wake up and semaphores. So which of the following options is correct? I'll number them so that you can answer 1, 2, 3. So when more than one processes are waiting, when there are contending processes, that means the processes which are waiting to enter in the critical section, uh, and all of them are contending to enter in the critical section. And when the critical section becomes free, at that time, wake up call is executed. So it will wake all the processes at the same time. So this problem, this is called dash problem, and this can be solved using dash. Any answers for option? Okay, so this is so here the right option is one, thundering herd problem and process queue. So this problem here when all the processes are woken up at the same time is called thundering herd problem, and process queue can solve this problem um, because if you maintain a process queue, that is, if you maintain whenever the processes are coming and they're trying to access the critical section, so you will put that process. If P1 comes, you that process is trying to enter the critical section, you put that in a queue. Then P2 comes, then you put that in a queue. So you, in this manner, if you maintain a queue, and whenever wake up happens, then you wake up. Whenever the wake up call is executed, then you look at the queue and you can wake up the process which is waiting, the first process in the queue. So in that manner, you can avoid waking up all the contending processes at the same time if you maintain a process queue. Okay. And lost wake up is different. Lost wake up means that if a wake up call was executed, but the wake up call was missed. So the process which is waiting did not receive the wake up call, then that is called a lost wake up. Okay. Any doubt? Okay. Okay, so the next one is, in a certain application, the initial value of a counting semaphore S is 20. The following operations were completed on the semaphore in the given order: 5P, 20P, 2V, 15P, 5V, 10P, 1V. So P here are down operations, V are up operations. So P's are request, and V is release. So when you acquire the lock, that is P. To acquire the lock, we execute P operation, and then to release the lock, we execute V operation. So the new value of the counting semaphore when all of these operations are done on the semaphore is dash. So initially your value is 20. Whenever you do a P operation, the value is decremented by 1. Whenever you do a V operation, it is incremented by 1. So if you do all of these operations, then what will be the value of the counting semaphore? Any answers? So how will you solve this? So S here is 20. Okay, so when you do 5P, that means 5 times down. So 5 times you are going to decrement. So if you decrement 5 from 20, it will become 15. Now you have next 20P. So you will again do 20 decrements, 20 downs. Okay, 20 decrement. Next, you will have V. So you will then increment. So if you do these operations, then you finally you will have a numeric value, and that value is being asked in the question. Any answers? Okay, so initially it is 20. So then 20, you have 5 P's. Okay, 5 decrement. So you can subtract 5 from 20. So it will become 15. Now when it has become 15, another 20 P's are there. That means another 20 processes are requested to acquire the lock. But the current value of semaphore here now is 15. So 15 minus 20 will become minus 5. Okay, now 2V means two processes released the lock, and so you increment the value. So current value here is minus 5 plus 2 will become minus 3. Now value become minus 3, but another 15 downs are there. So minus 3 minus 15 will become minus 18. So current here value is minus 18. Now 5 V's. So 5 locks were released. So 5 ups will be done. So 5V on minus 18. So minus 18 plus 5 will become minus 13. Minus 13, and then you have 10 P's. So again 10 downs. So 10 downs means minus 10. So current value is minus 13. Minus 13 minus 10 becomes minus 23. And then one lock is released, so plus 1. So minus 23 plus 1, the value will become minus 22. Okay. So the new value of the counting semaphore here is minus 22. Is that clear? Yeah, that's right. Yeah, so the new value here of the counting semaphore is minus 22. Okay. Next question is also similar. Here, consider the notation NP and NQ to indicate N down operations and M up operations on a semaphore respectively. For an application using a counting semaphore, the following sequence of operations is obtained: 5P, 2V, 10P, 5V, 4P. The value of the semaphore at the end of these operations is minus 7. What is the initial value of the semaphore? So you can solve this similar to the last problem. Okay, any answers? Yeah, you can try to solve it from the back also, but also you can simply assume a value of semaphore, say S, and then you can do all these operations, and then you can equate it to minus 7 and calculate the value of S. Okay, so we can solve it like this, that these are the operations: 5P, 2V, 10P, 5P, 4P. Select the initial semaphore value is S. So when you will do this operation on the semaphore, then S is initial. Then after the first operation, it will become S minus 5. Then 2 ups will means you will do plus 2, then minus 10, then plus 5, then minus 4, and this in the end it is said that the final value is minus 7. So this is equal to minus 7. Okay, so then you can just do this, and your S is equal to minus 7 plus 14 minus 2. So it will be 5. Okay. So your initial semaphore value was 5. So any question? Yeah, that's right. Okay. So the next problem here is if the value of a current value of a counting semaphore, so I think the statement is a bit wrong. If the current value of a counting semaphore S is equal to minus 2, what does this imply? First is the number of processes that can enter the critical section is 2. Second, number of processes blocked from entering the critical section is 2. The number of processes that can critical section and remain in blocked state is 2, and none of the above. So if semaphore value is minus 2, counting semaphore value is minus 2, then what does this signify? Any answers? So here the answer would be option number 1. Can anyone get that? They are in waiting queue. Yeah, they are waiting for to enter in the critical section. Yeah, so they are the number of processes. So they are the blocked processes, the processes which are want to enter the critical section. So minus 2 signifies that the number of processes, yeah, so option number 2, the number of processes blocked from entering the critical section is 2. So correct answer here is option 2. So that means two processes are blocked from entering the critical section, or two processes are waiting to enter the critical section. And that's it. Okay. Okay, so these were the questions that we had, but I think first two questions were, I think a number of people had missed the first two problems. So this question is, a critical section is a program segment, first which should run in a certain specified amount of time, second which should avoid deadlock, third which must be enclosed by a pair of semaphores P and V, and fourth one is where shared resources are accessed. So which is true? What is true about critical section? 1, 2, 3 out of these 4. A critical section is a program segment which should run in a certain specified amount of time, which should avoid deadlock, which must be enclosed by a pair of semaphores, and where shared resources are accessed. First, Any other answer? Okay. Hmm. So actually, so here the correct answer is option 4. So all of the, so far what you've learned, I think, uh, I mean, what if you think about what you've learned is that there is a shared resource, okay? And if multiple processes are trying to access the shared resource at the same time, then it can lead to uh, inconsistent inconsistency. Okay, so critical section is that program segment which where the shared resources are accessed, and that critical section, that is that part of the program segment, need to be need to be synchronized. So some mechanism is required in place to ensure that multiple processes do not enter the critical section at the same time. That is mutual exclusion, and progress and bounded waiting are there. So but if you, so looking at option one, 2, 3, the first option is which should run in a certain amount of time. So there is no limit on the amount of time that the process can spend in a critical section. So process can take as long as it needs in the critical section. So it's not, there is no specified time for that. It's not specified. So I'm sure you would not have read anywhere that critical section can be say only 10% of the execution time of a process. No, there is no amount of time specified. Okay, then which should avoid deadlock. So critical section program segment itself doesn't avoid deadlock. It is not critical section, it is not, I mean, the program segment which avoid deadlock is not called critical section. For deadlock we have different, we need different mechanisms, say use of mutexes and locks to avoid deadlock, but that is not the critical section. And the third option, which must be enclosed by a pair of semaphores, is also not, it's not true, because it is not necessary that the critical section has to be enclosed by a pair of semaphore. It can be, you can use other synchronization constructs like mutex locks to ensure mutual exclusion, progress, etc. Okay, so it's not necessary that semaphores have to be there. So 1, 2, 3 are not true in context of critical section. Only option number 4 is true, that critical section is the program segment where shared resources are accessed. Okay, and the problem one was that which of the following conditions could occur due to lack of synchronization. So if we do not synchronize the access to the shared resources, then which of the conditions can happen? First is inconsistency, second is loss of information, third is deadlock, and fourth is all of these. Hmm. Okay, critical section. So if I give you example, so if we have when, so when we looked at example of, we took this example, right? This question was there that you have this array of elements and you have 10 threads which are accessing this array, and then they are taking sum of elements which are assigned to these threads, and once they have taken the local sum, then they are adding the local sum to the total sum. Now here this total sum variable is shared. So this total sum variable is shared among all the threads. So since this is shared among all the threads, we need to ensure that only one thread can access it at a time. And that is why this total sum is variable is part of your critical section. Operation on this is part of like addition, adding or reading values of total sum is part of the critical section. Accessing the total sum is part of reading, part of the critical section, because this is shared among multiple threads and they can modify it. Now, if you take example of a normal system, uh, then it can be saved. You have only one hard disk, and so you have a hard disk and say only one process can read file from that. So then you will have to uh, so there only one process can do it, because the so that's, I think, the limitation on the resource itself. But if it is possible, say you have a resource, uh, how, I'm trying to think of a resource. Hmm. Or you can just think of a file. So if you have two processes and they have one file which is shared among both of them, okay? So if, say, process 1 is writing to that file and process 2 is also writing to that file at the same time. Say process 1 is writing uh, some, say, numbers 1 to 10, and process 2 is writing, say, numbers from 100 to 200. Now, if both of them tries to write simultaneously, then it is possible that process 1 will write value 1. Both, since, okay, I will just here write. But I think you understand the inconsistency, like why inconsistency can happen. Okay, critical section just means a piece, like some part of the code, part of your code which is accessing any shared resources. Okay, shared resource. So shared resource can be anything. It can be a device also, it can be a file also, it can be some local, say some program data also, like this array or variable. Okay, so if it is, say, a file, okay, there are two processes, P1 and P2, and there is a file. Okay, you say here we have a file, and process P1 is also trying to write to this file, and process P2 is also trying to write to this file, say, at the same time. So let's say this this file pointer is here. Pointer means that file is filled till here, and the processes will the next time the process write, it will start writing from this point. Okay, so if P1 reads that the pointer is pointing here, and at the same time, and say the pointer here means 100, so location is 100. Okay, 100th byte in the file. So if P1 reads that the location pointer is currently 100, and P2 also, say, reads that it is 100, and if they both simultaneously starts writing, so if it is writing some 10, 20, 30, 40, some values like this, and it is writing some values, say 1000, 2000 or something, then the values which will be written here, they will not be in order. It can be writing 10, then this one will be writing, say, 100, 1000, this, then it might be writing 20, then this might write 2000. So it is either possible that the information will be mixed up, or it is possible completely that if both of them uh, have accessed the pointers at the same time, and if the pointers are read at the same time, then it is also possible that they will overwrite their data. If P1 has written some data, it is possible that P2 will overwrite that data. So P1's data will be lost. So critical section only means any part of your code. If you're writing an application, okay, so if you as a developer, if you're writing an application and if a part of your application is accessing resources which are shared with the other application, or if your code itself has say multiple threads and those multiple threads are accessing some variable, some data, some file, or some device simultaneously, if they can access, then you need to synchronize the access to that shared resource so that only one thread can access the resource at the same time. Because when we do not synchronize, then problems can arise, like you correctly pointed out here, inconsistency can happen, loss of information, deadlock can also happen. Is that clear? Deadlock can happen in situations similar to when similar to, I think you must have seen example of semaphores. So if there are two resources, say R1 and R2, and there are two threads. So if thread 1 takes the resource R1 and thread 2 takes resource R2, but the threads need both of the resources, say, to compute, to finish the computation, then now both the threads will have one of the resources. Okay, I'll just write this down also here. Say you have two threads, th1 and th2, and you have here two resources, r1 and r2. Okay, let's say there is some operation which requires you to reuse both the resources. So thread 1 is working and thread 2 is also working. Thread 1 also needs both the resources and thread 2 also needs both the resources to finish some computation. Okay, so if thread 1 requests R1 first, so it will be allocated R1, and if thread 2 requests R2 first, it will be allocated R2. Now thread 1 will try to access R2, but it will be denied because this is already in use. Similarly, thread 2, okay, the arrow here I should make from here. And now thread 2 will try to access R1. It will also be denied because it is already allocated to T1. Now both of them will be deadlocked here because both of them have acquired one of the resource. Now they will not release the resource until they have finished the job. So both are waiting for one resource while they have taken one resource. So this is a deadlock situation which is arising here because we have not synchronized. So if we had taken a lock initially and then we had requested the resources, then this problem would not have arisen. So deadlock can also happen due to lack of synchronization. Okay, so that is all. These were all the questions that I had for today. So if you have any doubts, you can ask me. If not, then we can close the session. Any doubts? Yeah, hi. Sorry, can you repeat? I am not understanding the question. You're saying something about classes. Okay, okay. So the class is actually, this is a tutorial session, problem solving session. So it happens every Saturday actually. So my session is, so there are two sessions, but both of them are on Saturday. One is on Saturday 3 p.m., another is on Saturday 4 p.m. Unfortunately, I could not take my session yesterday, so today I'm taking uh, a session because of that. It was rescheduled to today. But the next session will happen on Saturday, 3 p.m. and 4 p.m. Does that answer your question? Sorry, but there is a your audio is breaking. Can you write your question in the chat box? Then I'll take it from there. And as Kushi pointed out, so if you go to your course web page, I think it's open. It's not open here. Mm. Yeah, if you go to your course web page, then in the end of the course web page, have you enrolled for the course? If you've enrolled for the course, then you can log in. Have you logged into the course on Swayam portal? Then you should be able to see all the assignments there. And in the end of the, I'm not very sure about the exam. So actually, I do not have any information about the exam, uh, like what type of questions will be asked. But your assignments are quiz type questions, and I'll see. Uh, I'll check if I can get any information about the exam. So if you've missed an assignment deadline, I do not think there is possibility to submit the assignment after the deadline, but you can submit the rest of the assignments. And okay, okay, okay. Thank you so much for joining. And okay, assignment. So I think you should. Okay, I'll just end. First, I'll stop the recording and maybe then I can show you.